April 14th, 1945, Oberammergau, Bavaria. The American soldiers descended into darkness. Behind them, the alpine sunlight painted the Bavarian mountains in shades of gold and green, but ahead lay only the throat of the mountain itself, a tunnel driven deep into living rock, sealed with steel doors that bore no markings, no warnings, no acknowledgement of what lay within. Captain Robert Jameson of the Third Army's Technical Intelligence Unit had seen much in the final months of the European War. He had walked through the rubble of Frankfurt and stood in the silent factories of the Ruhr. But nothing had prepared him for this. The tunnel stretched beyond the reach of their flashlights, and from somewhere in that manufactured abyss came the smell of oil and burned metal and something else, the acrid chemical tang of recently destroyed documents. On the tunnel floor lay scattered papers, some still smoldering. Jameson bent down and picked up a fragment. The edges were charred black, but enough remained to make out a technical drawing, a cutaway view of some kind of turbine assembly, annotated in German, with calculations he couldn't read. Further down the passage, his men found the first machine. It sat on a wheeled cradle, partially dismantled, its compressor blades catching the light like the teeth of some industrial predator. One of the soldiers whistled low. "What the hell is that, sir?" Jameson didn't answer immediately. He had been briefed on German jet engines before the crossing of the Rhine. He knew about the Jumo 004 and the problems with turbine blade failures. He had seen intelligence photographs of the Messerschmitt 262 and understood that the Germans had put jets into combat months before anyone else. But this machine was different. Its configuration was unfamiliar, its proportions wrong in ways he couldn't quite articulate, and scattered around it were tools still warm to the touch, as if the engineers had been working moments before the Americans arrived and had fled only at the sound of approaching boots. "Get the photographers down here," Jameson said quietly, "and find me someone who reads German. I want to know what they were building." The story of Germany's jet engines does not begin in those dark tunnels beneath the Bavarian Alps. It begins more than a decade earlier, in the minds of men who dared to imagine that the future of flight had nothing to do with propellers. In the 1930s, aviation had reached a kind of ceiling. Piston engines and propeller blades could only push aircraft so fast before the laws of physics intervened. As propeller tips approached the speed of sound, they lost efficiency catastrophically. Designers knew that if aircraft were ever to fly faster than 500 miles per hour, a fundamentally different form of propulsion would be required. The concept itself was simple enough. Take air from the front of the engine, compress it dramatically, mix it with fuel, ignite the mixture, and let the resulting explosion exit through the rear at tremendous velocity. The principle was reaction propulsion, the same force that makes a balloon fly across a room when you release it. But turning that simple concept into a functioning machine proved to be one of the most difficult engineering challenges of the 20th century. The problems were almost overwhelming. The compressor had to spin at speeds that would tear apart most metals known at the time. The combustion chamber had to maintain a stable flame at temperatures that would melt steel. The turbine blades that extracted energy from the exhaust had to survive in an environment that combined extreme heat with enormous centrifugal forces. And all of this had to happen inside a machine light enough to fly. In Britain, Frank Whittle had been thinking about jet engines since his days as a cadet at the Royal Air Force College in Cranwell. By 1930, he had written a thesis describing a gas turbine engine for aircraft, and by 1937, he had built a working prototype. But the British Air Ministry showed little interest. They were focused on improving existing piston engines and saw Whittle's invention as too radical, too uncertain, and too expensive. Whittle continued his work anyway, funding it with private money and his own relentless determination. But progress was painfully slow. In Germany, a young physicist named Hans von Ohain was arriving at similar conclusions through a different path. Ohain had studied aerodynamics at Göttingen University, where he became convinced that propellers had reached their limit. Working with the support of Ernst Heinkel, one of Germany's most innovative aircraft manufacturers, Ohain developed his own jet engine design. Unlike Whittle, Ohain had the backing of a major industrial concern from the beginning. Heinkel understood that whoever mastered jet propulsion first would dominate the skies of the future, and he was willing to pour money and resources into making it happen. What neither Whittle nor O'Hine knew at the time was that they were racing each other. The development of the jet engine would become one of the great parallel innovations of the war, two men on opposite sides of a coming conflict, both chasing the same impossible dream, neither aware of the other's existence. On August 27, 1939, just days before Germany invaded Poland and plunged Europe into war, test pilot Erich Varsitz climbed into the cockpit of the Heinkel He-178 at the Rostock-Marienhähe airfield. The aircraft was small and experimental, built around O'Hine's He-S-3B engine. It looked more like a child's sketch of an airplane than a functional machine. A stubby fuselage with straight wings and a single air intake in the nose. Heinkel and O'Hine stood on the edge of the runway watching. They had told almost no one about this test. The Luftwaffe High Command didn't know. The Reich Air Ministry didn't know. Even most of Heinkel's own engineers had been kept in the dark. This was too important and too uncertain to risk interference from bureaucrats who might shut the program down before it proved itself. Warsitz ran through his checks and pushed the throttle forward. The engine spooled up with a rising whine completely unlike the roar of a piston engine. There was no propeller vibration, no rhythmic pulse of cylinders firing, just a smooth, steady scream of compressed air and burning fuel. The He-178 began to roll. It accelerated faster than any conventional aircraft Warsitz had flown, the thrust pushing him back in his seat. The runway blurred beneath him, and then the wheels lifted, and for the first time in human history, an aircraft flew powered by nothing but the reaction of hot gases rushing backward through a turbine. The flight lasted only a few minutes. Warsitz circled the field once and brought the aircraft down, but the point had been made. The age of the jet had arrived. The problem was that almost nobody cared. When Heinkel finally arranged a demonstration for Luftwaffe officials, they watched politely and then explained that Germany already had excellent fighters and bombers. The He-178 was interesting as a research project, they said, but it had no immediate military application. Ernst Udet, the director of Luftwaffe development and a First World War flying ace, was more blunt. He told Heinkel that jet engines consumed too much fuel, required too much maintenance, and offered no advantage over existing designs. The Luftwaffe had no interest in pursuing them. It was a catastrophic misjudgment, one that would haunt Germany throughout the war. But in 1939, with the Wehrmacht smashing through Poland and France in campaigns that lasted weeks instead of years, there seemed no reason to invest in radical new technologies. Germany's existing aircraft were more than adequate for the task at hand. By the time the Luftwaffe realized it had made a mistake, it would be far too late. The war changed everything. After the fall of France in 1940, the Luftwaffe found itself locked in a grinding campaign of attrition with the Royal Air Force. The Battle of Britain exposed the limits of German fighter design. The Messerschmitt Bf 109, for all its strengths, couldn't escort bombers deep into England and return with enough fuel to fight effectively. German bombers were vulnerable, and losses mounted. Then came the invasion of the Soviet Union in June 1941, and suddenly Germany was fighting on two fronts against enemies with vast industrial resources. By 1942, British and American bombers were beginning to strike targets inside Germany itself. The Luftwaffe needed faster fighters that could climb quickly, intercept enemy bombers before they reached their targets, and get back on the ground before running out of fuel. Suddenly, jet propulsion didn't seem like an impractical experiment anymore. It seemed like the only way forward. The man who would make German jet fighters a reality was not Hans von O'Hine, whose He-S-3 engine had proven the concept, but remained too weak for combat use. It was Anselm Franz, the chief designer at Junkers, who created the UMO 004, the engine that would power Germany's operational jet aircraft. Franz understood that a military jet engine couldn't be a delicate laboratory prototype. It had to be mass-produced by workers with limited skills, using materials that Germany actually possessed. Chromium, nickel, and other heat-resistant metals were in desperately short supply, reserved for tanks and artillery. Franz would have to design an engine that could function without them. The solution he devised was both ingenious and tragic. The JUMO 004 used mild steel for its turbine blades instead of exotic alloys. To prevent them from melting, Franz coated them with aluminum and accepted that they would only last for 25 hours of operation before failing. An engine with a service life measured in hours was unthinkable by peacetime standards. But Germany was no longer at peace. If a jet fighter could fly 10 missions before its engine needed replacement, that was enough. The Jumo 004 was not an elegant machine. It was a brute force answer to an impossible problem, a device that sacrificed longevity for immediate functionality. But it worked. In the summer of 1944, the Messerschmitt Me 262 entered service with the Luftwaffe. It was a revelation. With two UMO 004 engines slung beneath swept-back wings, the 262 could reach speeds of 540 miles per hour, nearly 100 miles per hour faster than any Allied fighter. It could climb to altitude in minutes, flash through a bomber formation with its 430mm cannons blazing, and disappear before escort fighters could react. Allied pilots who encountered it described the experience in near mystical terms. One American bomber gunner reported seeing what he thought was a German fighter diving to attack, only to realize with shock that it was climbing almost vertically so fast that his perception had inverted. Another pilot said it was like being hunted by something from the future. But the 262 arrived too late and in too few numbers to matter. Only about 1,400 were built before the war ended, and mechanical problems kept most of them grounded. The Jumo 004 engines were as unreliable as France had feared. They flamed out without warning. Turbine blades disintegrated in flight. Fuel lines cracked. Pilots joked grimly that the greatest danger in flying a 262 was not Allied fighters but the engines themselves. And yet, even with all its problems, the Me 262 changed everything. Allied intelligence officers who examined captured examples understood immediately that Germany had leaped a generation ahead in aviation technology. The question that haunted them was simple. What else had the Germans developed? What other machines were hidden in those underground factories? And how far ahead had German jet research actually gone? The Heinkel Hies 011 represented the next generation of German jet engines. While the Jumo 004 was a stopgap measure using inferior materials and accepting short lifespans, the HES 011 was designed to be everything a jet engine should be: powerful, efficient, and reliable. It featured an axial compressor with advanced blade geometry, a two-stage turbine, and an afterburner that could boost thrust for short periods. On paper, it promised nearly twice the power of the Jumo 004 with significantly better fuel economy. Engineers who worked on the project believed it would have given German fighters an overwhelming advantage if it had entered production a year earlier. But by the time the first HES 011 prototypes ran successfully in early 1945, Germany was collapsing. Allied armies were crossing the Rhine. Soviet forces were closing on Berlin. The factories that might have produced the HES 011 in quantity were rubble, or soon would be. A handful of prototype engines were completed. Some were tested, most were destroyed by retreating German forces to prevent them from falling into Allied hands. But the HES 011 proved that German engineers understood the principles of advanced jet propulsion as well as anyone in the world, and in some respects better. The question was whether they had gone even further, whether somewhere in those final desperate months they had created something more advanced still. Behind the programs that made it into production lay a shadow world of experimental designs that ranged from the ambitious to the nearly impossible. German engineers, freed from peacetime constraints and driven by the desperation of a losing war, explored concepts that would not reappear in Western aviation for decades. The Focke-Wulf Project. I was an attempt to create a single aircraft powered by three different types of engines: a turbojet for cruise flight, a rocket for rapid acceleration, and a ramjet for high-speed dash. It existed mostly on paper, a series of blueprints and calculations that described an aircraft that would have been almost impossible to fly and even harder to maintain. But the fact that serious engineers spent time on it showed how far Germany was willing to push the boundaries of what seemed possible. The Kronach-Loren ramjet went even further into speculative territory. Ramjets were conceptually simple. Air entered the front of the engine, was compressed by the forward motion of the aircraft itself, mixed with fuel and ignited, then exhausted out the back. No moving parts, no turbines, just a hollow tube that turned speed into thrust. The problem was that ramjets didn't work at low speeds. An aircraft equipped with one needed some other form of propulsion to reach the velocity where the ramjet became effective. The Kronak-Loren attempted to solve this by using coal dust as fuel, which could be stored more densely than liquid hydrocarbons. Tests were conducted, models were built, and then the war ended and the project vanished into history. The Focke-Wulf Ta-283 was perhaps the most ambitious of all. It was designed as a high-altitude interceptor that would use a rocket engine to climb nearly vertically to 50,000 feet, faster than any bomber formation could react, then glide back down while firing its weapons. A small turbojet would provide power for the landing approach. The entire flight profile would last less than 10 minutes from takeoff to touchdown, but in that time, the Ta-183 was meant to destroy multiple enemy aircraft and return safely. Wind tunnel tests suggested the design was aerodynamically sound. Calculations indicated the engines would work, but building it would have required materials, manufacturing capacity, and fuel that Germany no longer possessed. Like so many late-war German projects, the Ta-283 represented extraordinary engineering applied to a strategic situation that was already hopeless. And yet, Allied technical intelligence officers who examined these designs after the war treated them with great seriousness. These were not the fantasies of desperate men. They were carefully calculated proposals from some of the best aeronautical engineers in the world, and they provided a roadmap for what jet aviation might become in the decades ahead. As Allied bombing intensified in 1943 and 1944, Germany faced a crisis. Its aircraft factories were being systematically destroyed. Thousands of workers were being killed in raids. Production was collapsing. The solution the Nazi regime devised was as brutal as it was effective: move production underground. In the mountains of central Germany, slave laborers dug vast tunnel complexes where aircraft could be assembled beyond the reach of bombs. The WWII factory complex near Kalle was one of the largest. Driven deep into the Walpersberg mountain, the facility consisted of miles of interconnected tunnels where Me-262 jet fighters were assembled by workers who never saw daylight. Prisoners from the Buchenwald concentration camp were marched to the site each day and worked until they collapsed. Thousands died from exhaustion, malnutrition, and outright murder. The tunnels were cold and damp, lit by harsh electric lights, and filled with the constant noise of machinery and human suffering. Another complex existed at Oberammergau in Bavaria, where Messerschmitt maintained a secret facility for experimental aircraft development. This one was smaller but more heavily guarded, accessible only through tunnels whose entrances were concealed and protected by SS troops. Workers who entered signed documents swearing them to absolute silence. Security was so tight that even Luftwaffe officers were turned away if they lacked the proper authorization. What exactly was being developed at Oberammergau remains partially unknown to this day. Some documents survived. Some workers lived to tell their stories after the war, but large gaps remain in the historical record, gaps that have fueled speculation for 80 years. As the war entered its final weeks, engineers at these underground facilities received orders to destroy anything that might be useful to the Allies. Machines were smashed, documents were burned. In some cases, entire sections of tunnels were collapsed with explosives, burying whatever lay inside beneath tons of rock. Workers later reported that some equipment was not destroyed but hidden, sealed inside tunnels, covered with rubble, or removed to locations that were never recorded in any official document. Whether this was done on orders from above or was the desperate improvisation of engineers who couldn't bear to see their life's work obliterated, no one can say for certain. When Captain Jameson and his team entered the Oberammergau tunnels in April 1945, they found a scene of organized chaos. The Germans had clearly tried to sanitize the site before abandoning it, but they had run out of time. Some machines remained intact. Others had been partially dismantled, as if the workers had been interrupted mid-task. The most valuable find was not the hardware, but the papers. Despite the burning and the shredding, thousands of technical documents survived. Drawings of engine components, test data, maintenance logs, letters between engineers discussing problems and solutions, and scattered among these routine materials were fragments of something else. References to projects that had no names, only code numbers, and descriptions of performance characteristics that seemed impossible even by the advanced standards of German jet development. One document, badly burned around the edges, described an engine with a thrust-to-weight ratio far superior to anything the JUMO 004 or HES 011 had achieved. Another mentioned a novel compressor design that would allow much higher pressure ratios without the risk of blade failure. A third referenced materials testing for turbine blades that could supposedly withstand temperatures hundreds of degrees higher than existing alloys. Taken individually, these fragments might have been dismissed as speculative research or misunderstood data. But taken together, they suggested that German engineers had been working on jet engine designs significantly more advanced than anything that had reached production. The question was whether these projects had remained on paper or had progressed to the prototype stage. Operation Paperclip began even before the war officially ended. American intelligence teams raced across Germany, searching for scientists, engineers, and technical documents before the Soviets could claim them. The focus was on rockets. Werner von Braun and his V-2 team were the biggest prizes, but jet propulsion was a close second. The U.S. Army Air Forces understood that whoever mastered jet technology first would dominate military aviation for the foreseeable future, and Germany had a 10-year head start. Engineers from Junkers, Heinkel, Messerschmitt, and BMW were rounded up and interrogated. Most cooperated eagerly, seeing American employment as preferable to Soviet captivity or war crimes trials. They were flown to the United States, given security clearances, and put to work on American jet programs. Their knowledge would shape the development of aircraft like the F-86 Sabre and the B-47 Stratojet, designs that borrowed heavily from German research. The Soviets conducted their own operation with equal determination and less concern for legal niceties. Entire factories in the Soviet occupation zone were dismantled and shipped east. Engineers who had worked on German jet projects were offered positions in the Soviet aviation industry, and those who declined the offer were taken anyway. The Mikoyan-Gurevich MiG-15, which would become one of the most successful jet fighters of the Cold War, owed much of its design to German research. Its swept wings, its engine configuration, even its armament layout showed the influence of captured Me-262 studies. But despite this massive transfer of knowledge, both American and Soviet intelligence officers believed they had not captured everything. There were too many gaps in the documentation, too many references to projects that had no corresponding hardware or blueprints, too many engineers who seemed to be describing work they had witnessed but could not fully explain. The possibility remained that somewhere in the chaos of Germany's final collapse, some pieces of advanced jet technology had been hidden rather than destroyed, secured by men who hoped they might bargain with it after the war, or simply could not bear to see it obliterated. No aircraft has fueled more speculation about hidden German technology than the Horten Ho 229. It was not, strictly speaking, a jet engine project. It was an aircraft design, a flying wing with no conventional fuselage or tail, powered by two JUMO 004 engines embedded in the wing itself. But the Ho 229 represented such a radical departure from conventional aircraft design that it became the centerpiece of theories about German technological leaps that were supposedly decades ahead of their time. The Horten brothers, Reimar and Walter, had been experimenting with flying wings since the 1930s. They believed that eliminating the fuselage and tail would reduce drag dramatically, making aircraft faster and more efficient. By 1944, they had convinced the Reich Air Ministry to fund a jet-powered version that could serve as a fast bomber capable of reaching England and returning without refueling. Several prototypes were built. One crashed during testing, killing the pilot. Another was nearly complete when American forces captured the Horten factory in April 1945. That aircraft was carefully disassembled, crated, and shipped to the United States, where it eventually ended up at the Smithsonian's National Air and Space Museum. In the decades after the war, the Ho 229 acquired a mythology that far exceeded its actual capabilities. Authors and television documentaries claimed it was the world's first stealth aircraft, designed to be invisible to radar. Some went further, suggesting it incorporated materials and design principles that would not reappear until the F-117 Nighthawk in the 1980s. The truth, as determined by careful analysis at the Smithsonian, is more nuanced. The Ho 229's flying wing configuration did give it a smaller radar cross-section than conventional aircraft, simply because it lacked large vertical surfaces that reflected radar waves directly back to the transmitter. And the Hortens had mixed charcoal and sawdust into the wood-based composite material used for the wing skin, which absorbed some radar energy. But tests using modern radar systems showed that a 1940s radar installation would have detected the Ho-229 at a range only marginally shorter than it would have detected a conventional aircraft. The Ho-229 was not invisible, it was simply slightly harder to see. Where the mythology contained a grain of truth was in the concept itself. The Hortens understood that radar detection was becoming a critical factor in air combat, and they had taken steps, however primitive, to address it. That understanding was decades ahead of mainstream military thinking. Whether they fully grasped the implications of what they were doing or had stumbled onto stealth principles almost by accident remains debated among historians. The idea that Germany hit a revolutionary jet engine, something beyond the HE-S-011, beyond anything that has appeared in the historical record, rests on several pieces of circumstantial evidence. First, there are the gaps in the documentation. Historians have identified numerous projects that are referenced in surviving German documents, but for which no detailed technical information exists. Project numbers that appear in production schedules, but have no corresponding blueprints. Engine designations mentioned in letters that don't match any known design. Budget allocations for research programs whose purpose was never recorded. Second, there are the testimonies of engineers and workers who claimed after the war that they had seen or worked on advanced jet engines that were not among the equipment captured by the Allies. Some described engines with unusual configurations, contra-rotating turbines, multi-spool designs, or exotic cooling systems. Others spoke of materials they didn't recognize, possibly experimental alloys developed in secret research programs. These accounts are difficult to verify. Memories fade and become corrupted over time. Some witnesses may have exaggerated their knowledge to seem more important during post-war interrogations. Others may have been describing equipment they misunderstood or saw only briefly. Third, there is the behavior of the German engineers themselves in the final weeks of the war. Multiple sources describe efforts to hide technology from the advancing Allies. Not destroy it, but conceal it. One account tells of a Junkers engineer who supervised the removal of a prototype engine from a testing facility and its transport to a location in the Austrian Alps, where it was supposedly hidden in a cave. The engineer died in the 1970s without ever revealing the exact location, and no subsequent searches have found anything. Another story involves Messerschmitt personnel at Oberammergau who allegedly sealed part of the tunnel complex with explosives, trapping equipment inside. American forces who arrived days later found the collapsed section but chose not to excavate it, deciding that the effort wasn't worth the potential payoff. If equipment remained behind those tons of rock, it remains there still. Are these stories true? Impossible to say with certainty. The problem with secrets is that by their nature, they leave little evidence. If an engine was successfully hidden, then by definition, no one found it, which means there would be no documentation of its discovery. The absence of evidence is not evidence of absence, but neither is it proof that something existed. Historians have examined German jet development from every angle, searching for the engine that might have been hidden. The most credible candidate is an advanced version of the HE-S-011, possibly incorporating a two-stage compressor and improved turbine blade cooling. Documents suggest Heinkel was working on such a design in early 1945, though whether it progressed beyond the drawing board is unknown. If a prototype existed and was hidden, it would explain the references in surviving documents to performance characteristics beyond what the standard HE-S-011 achieved. Another possibility is that the hidden engine was not a complete design, but rather a collection of advanced components. An experimental compressor here, a novel turbine blade design there, perhaps an innovative combustion chamber, that were hidden separately and have never been reassembled into a complete picture. German jet development was not a single linear program, but a web of interconnected research efforts. Components developed for one project were often adapted for use in others. A revolutionary compressor design might have applications in half a dozen different engines. If the engineers who understood how these pieces fit together were scattered by the war's end, their knowledge might have been lost even if the physical components survived. The British Aeronautical Society conducted its own investigation in the 1950s, interviewing former German engineers and reviewing captured documents. Their conclusion was carefully worded. They found no definitive evidence that a revolutionary jet engine had been built and hidden, but they acknowledged that gaps in the historical record made it impossible to rule out completely. They noted that several promising research programs appeared to have been abruptly terminated in early 1945, with no clear explanation for why. Equipment inventories showed discrepancies. Machines that should have been at certain facilities were not there when the Allies arrived, and no destruction orders for them could be found. The Society's final report stated that if an advanced jet engine had been hidden, it was most likely buried in the Alps or sealed in one of the underground facilities that were never fully explored. But they emphasized that this was speculation, not evidence. The truth, they concluded, would probably never be known with certainty. What cannot be disputed is the profound impact German jet research had on post-war aviation. When American engineers began designing the first generation of U.S. jet fighters, they relied heavily on data captured from German facilities. Swept wing configurations, axial flow compressors, afterburner designs, all of these were refined or directly adapted from German work. The F-86 Sabre, which fought MiG-15s to a standstill over Korea and is often credited with maintaining American air superiority during the Cold War's first hot conflict, would not have been possible without German research. British jet development followed a similar path. Though Frank Whittle's engine had flown first, British designers incorporated German innovations to improve performance. The Rolls-Royce Avon and the de Havilland Ghost, engines that powered British jets through the 1950s, showed clear German influence in their design. Even Soviet aviation, which took a different developmental path, owed much to captured German technology. The Klimov VK-1 engine that powered the MiG-15 was a reverse-engineered copy of the Rolls-Royce Nini, but the Soviets had acquired German research data that helped them improve it beyond the original British design. In a very real sense, every jet that flies today is a descendant of the work done in Germany in the 1940s. The fundamental principles, axial compressors, turbine blade cooling, combustion chamber design, materials engineering, were established by men like Anselm Franz and Hans von Ohain under the pressure of war. Modern engines are vastly more powerful and reliable, the product of 80 years of continuous refinement, but they are refinements of ideas first proven in places like the Oberammergau tunnels. If a revolutionary jet engine lies hidden somewhere beneath the Alps, if it exists as anything more than fragments of burned documents and fading memories, it has kept its silence for 80 years. No deathbed confession has revealed its location. No accidental discovery has brought it to light. The mountains of Bavaria and Austria have been crisscrossed by hikers, developers, and treasure hunters, but none have reported finding sealed tunnels containing German jet engines. Perhaps it never existed. Perhaps the stories were the product of post-war confusion, exaggerated by witnesses who wanted to believe that their work had been more significant than it actually was. Perhaps the references in surviving documents describe research programs that never progressed beyond theoretical studies. Perhaps the gaps in the historical record are simply gaps, information lost in the chaos of collapse, not deliberately hidden, but simply destroyed or scattered beyond recovery. Or perhaps somewhere in the dark, in a cave whose entrance was concealed in April 1945, or behind a wall of rubble in a tunnel that was never fully explored, sits a machine that would have changed history had it arrived 6 months earlier. A jet engine with capabilities that matched or exceeded what Allied designers would achieve 5 years later. A device that represented the absolute pinnacle of 1940s German engineering, hidden not out of strategic calculation, but out of the simple human inability to destroy something you have spent years creating. We will probably never know. The men who might have answered the question with certainty are all dead now. The documents that would prove or disprove the story are ash or lost or hidden in archives that have not yet been fully explored. What we are left with is the knowledge that Germany's jet engine program represented one of the great technological leaps of the 20th century, achieved under conditions of total war and near-complete industrial collapse. Whether the program produced one final secret masterpiece or whether that masterpiece exists only in the imagination of those who wish history were more dramatic than it actually was, may be a question that can never be definitively answered. But on certain quiet evenings in Bavaria, when the sun sets behind the mountains and the shadows grow long across the valleys, it is possible to imagine an American captain descending into darkness, finding a machine he does not understand, and making a choice that changes everything. It is possible to imagine engineers working by flashlight in the final hours before surrender, sealing their life's work behind stone and steel. It is possible to imagine a secret kept so perfectly that it remains a secret still. Whether that imagination reflects truth or merely what we want truth to be is a question each person must answer for themselves. What is certain is that the jet engine, in all its modern forms, carries within it the legacy of those desperate years when Germany reached for the future and very nearly grasped it. The engines that power commercial airliners, military fighters, and spacecraft all descend from the work done in those underground factories, in those secret testing facilities, in those tunnels driven deep into living rock. And if somewhere in that lineage there exists a missing link, a machine that was hidden rather than destroyed, then it remains the last great secret of the Second World War, silent and waiting in the darkness, a monument to human ingenuity and the terrible costs of the conflict that called it into being.